Right, thanks for the introduction. I'm Michael, and today I'm talking about too many or too one, all in one. And essentially, I'm going into the talk with a conjecture that many data structure design and optimization issues, but as well programming language runtime optimization issues, can be efficiently tackled with an efficient encoding of type heterogeneity. And that paper in particular explores how you can craft data structures that use heterogeneity internally for optimizations. And in particular, I'm talking about functional data structures that are based on hash tries. Well, let me clarify a bit what I mean when I talk about heterogeneity in this context. Heterogeneity doesn't always have to be visible on the type signature or be present on the polymorphic type argument, for example. So in this case, let's assume we have a collection of arbitrary precision integers, not floating points, or maybe floating points, who knows. But from a programming language perspective, if you craft a runtime, you would like to store the values as concise as possible. So if you have arbitrary precision integers and it fits into 32-bit integer, we would like to store it as such, as a simple 4-byte value type. If it fits into 64 bits, we might store it as that. And if it's larger, well, we might need a more complex, maybe object for modeling that. In Java, that would be a big integer. So maybe on the type, we have a homogeneous type, but we can use and leverage some sort of decomposition internally in order to craft a data structure that's, for example, optimized in terms of memory footprint. So here it's really decomposition by runtime representation. So that's one kind of heterogeneity a data structure could optimize for. Another one is, well, let's assume we have a multimap and with just generic type arguments k and v, but we could do something internally in order to optimize by the arity of the tuples we have. So let's assume we have just mappings that are unique from key to value. We might not need to associate or allocate a nested set. We can store the value inline. But if the arity is bigger, we have 2, 3, 4 values associated with a key, well, then we need to handle that specifically. So that's a sort of heterogeneity that's also not visible outside, but that's exploited on the inside, on the data structure level. And what I'm presenting is how you can capture that kind of heterogeneity and craft a data structure that can optimize for that. The running example for the talk will be the multimap, but as said, there are many more of these use cases you might be interested or to consider. Because I'm talking about multimaps, I would like to take a step back and talk about collection data structures in general. So what are the characteristics of collection data structures? What are we looking for? Collections typically have a common set of data type abstractions. Let's say lists, sets, maps, what you all know and use in almost every program. And for every of these abstractions, they're typically just a small handful of highly optimized, handcrafted data structure implementations. So these are typically generic and general purpose. So they're not really tailored towards a particular workload or some sort of input data and whatnot. And they're typically also carefully balancing runtime characteristics. So say what's the memory footprint and how it behaves in terms of runtime performance. So they should be versatile. They are the Swiss Army knife that every engineer is kind of using. All right. From that perspective, a multimap is sometimes an odd fit, and you don't find it in that many collection libraries, at least. And the reason is very simple. Well, you can easily construct a multimap by just composing two primitives. You compose maps and sets. You use sets as the values as a polymorphic map, and then you have something like a multimap. You can deal with several values that are associated with a key. Well, some libraries out there, or some languages, they have multimaps. And most of them have multimaps just on the interface or type level. But essentially under the hood, you still have maps with nested sets. You just lift them with, for example, traits in Scala or protocols in Clojure to a much nicer API that you use as a programmer, but it doesn't change the runtime representation. You still have the explicit composition under the hood. And that's bad. that's really bad. That's suboptimal like for runtime performance, because you have two like basic blocks that you have to combine in a way in order like to fit all the invariants. Like for a multi-map, you want to like throw away once the set runs empty, so like you want to throw away the whole key value binding, and so on and so on. And if you look at code and implementations that try to like be more clever about that and optimize that, there's a lot of like external like calls and enforcing of invariants that's going on. But what's even more alarming is like it's also like not performant in terms of like memory footprints. So in my measurements, like what I figured out is like that on average on the JVM, let's say for implementations in Clojure and Scala, the typical overhead per key value tuple, like just storing 8 bytes of payload, like is 65 bytes. So you're spending 8 times the memory than like, like just in accidental overhead for encoding a multi-map. I would rather spend that like in like making my set bigger and like storing more payload there. All right, that's about like performance. But there are like things that you can't even do if you do like explicit composition. So in immutable collections, what you often find is a sort of builder pattern, where you use like a builder data structure to efficiently stage the construction of your immutable collection. And what does the builder do? It kind of like gives you a mutable interface where you can like have several like addition operations or like your insert operations as here. And in the end, you just convert like your builder to an immutable instance. And what here matters is how you convert like from the builder to the immutable instance. And there are implementations out there that are like pretty clever about like how doing that. Like most of the times, like it's like a constant conversion, or even like atomic, like when you just like freeze with a lock the content of the data structure. That's all right, but that's a map. And I would like really focus like on the multi-map use case. And there you see like how the abstraction breaks apart if you use like explicit composition. Because how do you structure your builder? Like if I want to create a multi-map, like, well, should I like have a set builder or set builders, like multiple of them, nested into a map builder? And how do I go like in converting that like to my final like immutable like instance? Well, here we really have an algorithmic problem, because we first would need to iterate over all the nested like set builders, close them before we can like close our map builder. And that's really an issue. And yeah. And that issue, you could say, could be solved if we have a native multi-map implementation that doesn't rely on explicit composition of maps and sets. Right. But should we? Should we add yet another data type to a collection library? Because the question is, so it takes a lot of like effort in order like to engineer it, like in order like to maintain it and so on. And as said, like the kind of like guiding principles is that you have a minimal set of abstractions that you keep there that are highly versatile. So like adding yet another data structure might not be the right approach. Well, let me take a step back and just once again look at the differences like between a map that's already in a collection library, like typically everywhere, and the multi-map. Essentially, the difference is, that in one case, I'm restricted to one-to-one mappings between keys and values. And in the other case, I'm free to associate multiple values with a key as well. So what about like, instead of adding yet another data type, like how about like having a generic data type maybe, or implementation that fits both? Like let's say that you can use like efficiently like as a map without the loss of efficiency. And that's a better multi-map because it's like inherently like knows something about multi-mappings as well. And that is what I would like to like present here, is like how you can like use the heterogeneity internally in order to distinguish like between like one-to-one and one-to-n tuples. And that's like one use case from Axiom, like the name of the data structure, what you can use it for. So let me talk a bit about Axiom's design. Well, and in order to do that, I would like to start off with something that's maybe like more familiar like to the audience here. I'm not sure like how many of you like implemented like hash tries or any kind of immutable data structures, but I guess all of you like once in the lives or maybe like in course of your curricula implemented a hash table like on a continuous array. So let's assume we want to store different heterogeneous types in that hash table. Well, we hash it, and like based on the hash code that comes out, we determine the bucket and the index, and there we store the element. And here, like color-coded, you would like the color stands for like a different type or like an element of a different type that we're storing there. We don't know anything about the ordering because like, well, it's dependent on the input on the hash code, so they might be arbitrarily mixed there. And yeah, and we have like one large continuous like array that's like large, so large that it can hold at least all of the elements and has some bigger room like for minimizing collisions. Well, in functional data structures, like usually you encode the same information, like not in a flat array, use it like a hierarchical information, hierarchical structure. And instead of having like one large continuous array, you have like smaller chunks that are like upper bounded in size. So for example, each like array here can just have like, or can grow to a size of like maximum 32. And that's like how you encode like the whole space of like in 32 hash codes there. In principle, it didn't change. Like still a hash code like that's depending like on runtime information like determines where you put your elements there. But essentially, we even like made our problem like a bit worse. So you see the green blocks there, they weren't there before. And that's like we're introducing like yet another sort of like heterogeneous type that we have to care of, because we have a tree, we have to somehow like store our link to subtrees. So essentially, like we started out with having two different like heterogeneous types. Now we suddenly have three, and we also like have some empty buckets. The core idea on a high level of Axiom is, well, to do a permutation on the content. So like permuting the elements that first of all we can get rid of like all the empty slots, and second of all we group together all the elements of the same type. So like there is no like that every color just occurs like once there, and that's essentially like done by associating like some sort of like metadata with all the cells in the array. So if you look at a node of the tree, like as you saw like before, in Java you would like represent it like sort of like simplified with, okay, you have like some sort of like storage, like content array like here, and then some sort of like metadata, and here it's a bitmap. And we use like a encoding like for bitmaps where we say, okay, we want like to tag different like different types there. And in our case, we want like to have like to one mappings, to many mappings, subtrees, and essentially we also like want to encode somehow like the slot is empty for compression. And we can do that in that case with 2 bits per slot. So essentially like a long bitmap like is sufficient in order like to create or like to cover all the tiles that we have there. So if you generalize that, well, let's say I do not want to just differentiate like between different internal like presentations of a multimap. You can say, well, you can use a bitmap there and like use log n bits like for n different like types that you would like to encode. Well, so what are the challenges like in doing this kind of like permutation? Well, one of the challenges is I need like now to find the offset of my category, like of my type, like which I want to access. I need to find the right position within that category, and that all in like in a manner, like in a reversible function that I maintain like the hash, like constant time, like hash lookup properties of a hash map. I'm not going like into details like how that works. Like I refer you to the paper about that, but I would like more to speak about like what you can win by using that data structure. And on a high level, like what you benefit is, well, you can improve like batch operations like vastly. So if you want to iterate over the data structure, stream, map, or like apply like a map operation on all the values, that's far more efficient because like instead of like having arbitrary mixing of like different types, you group them all together. And that means is you just like, you do not need individual type checks. You can like improve on that. And as I showed you before, all the empty like slots also go away. So like we optimize like for the sparsity of a hash map and can improve footprints there as well. And at last, there's also like the possibility, because you group all the elements of the same type together, that you can optimize, let's say, the memory representation, like a memory representation based on the type. So you can differentiate, for example, like int32s or any kind of arbitrary value types from memory, like from reference types, and so on. So just by default, like doing these permutations, Axiom is already like better than like these kind of explicit composed multimaps that I showed you before. So if you compare it like to similar implementations in Clojure and Scala, Axiom already gives you like a 1.7 times improvement, like in terms of like lower memory footprint. But that's just a start. Like we can even do better, like for the case of multimaps. So on the right, you see like a node, like with the metadata, like the bitmap, and like the content array, like below. But the collection data structure is typically more than just like the internal tree structure, like that's hidden away from you. So you also like have maybe like some instance that holds like some global metadata. So for example, like the size of your collection, how many elements do you store there, like other properties like the hash code of a collection. And if you have like one-to-many mappings in our collection, well, we also like need to have like nested sets that follow the same pattern, like probably. And here you already see like there's some sort of redundancy, because if we go away like from the explicit composition and like do internally like distinguish between different representations, we might not like be interested in the metadata of what's hidden away from the user. So like the size and the hash code of all like the nested things are maybe like not irrelevant. And once we remove that, we can get rid of like the whole like nested set there as well. So we can immediately point from like multi-map nodes, tree nodes, to like set tree nodes there. Okay, doing that like would give us like yet another benefit. So our data structures are now suddenly like roughly 2.4 times like smaller than if you would use the explicit nesting. And there's also like other techniques you can apply like in order like to further improve that. So for example, let's assume you specialize on how many like slots are occupied, for example, in your map. So like you emit specialized like memory layouts for different configurations, for like the multi-map node and for the set node, and suddenly you get like the improvements like 5 times over the competition. All right, that kind of like summarizes like footprints and like what you can do like for the multi-map use case. Now I would like to talk about like runtime performance. Well, I said like, okay, let's assume you have like a hybrid data structure that's like the best of both worlds. Like it can substitute like a regular map, then it should be like as performant as a regular map. And further on, like, so let's look at that use case first. So we are comparing like an Axiom multi-map. So that's actually capable of like being used as a map or as a multi-map against the state-of-the-art immutable data structure that's just a pure map implementation. So in that case, you see like it's scoring decently. So like for basic operations like lookup, you have an average like a slowdown of like 25% in that case, because like you have all the machinery like in order to distinguish different internal representations. But there are other like bulk operations, as I told you before, like iteration, that we can like vastly speed up there. Okay, so that's like the use case for a map. But now, okay, let's use it really as a multi-map and compare like apples to apples. In that case, well, if you compare it like to multi-map in Scala, we actually see that roughly for the basic operations, we can like improve by roughly like 25 to 50%. And there's like one exception, that's like the lookup for values that are not there, that are not present in data structure. Their Scala, for example, like treats memory in order like for caching certain results in order to speed up that use case. So there we're lagging behind. But let's compare it, for example, to the implementations present in Clojure, and there you see like performance is roughly like factor of 2 up to a factor of 3 like better than with like explicitly composed like maps and sets in Clojure. All right. So the last thing that I would like to tell you about is like, well, what kind of like challenges like did we have? So I told you like we use like multi-bit sequences for representing the metadata. And in standard libraries, you usually find like APIs that directly boil down to meshing instructions for bit counting and other operations that are like highly efficient. But it doesn't work for multi-bit sequences. And if in that example, for example, we would like to count all the 0, 0 like sequences, that's not something like we can do. So that's a typical operation, like in order like for the relative indexing. We would like to mark up all the 0, 0s, cancel out all the other information, and then, well, we can essentially like reduce the 2-bit sequences to 1-bit sequences, and then rely on our bit counting operations as well. That can be done like in software, or there's also like more like there's hardware support like in modern CPUs. For example, you could use like parallel bits extract and parallel bits deposit operations that are present in modern Intel CPUs. All right. All the other details like how like the mapping functions work and so on, they're in the paper. But I hope like you got like some glimpse in what you can do with the data structure. To summarize, well, I was presenting Axiom, data structure that you can use for encoding internal heterogeneity. I showed you like how it performs if you apply it like for a real use case, in that case multi-maps, and what kind of like challenges you have in doing the bit twiddling and optimizing that. So thanks for your attention. If you have any questions, I'm glad to answer them.
Your performance numbers were on a JVM implementation, or okay?
Yeah, that was JVM.
Any other question? Actually, I have one.
Okay,
It sounds like this may actually be an opportunity for a new sort of combinational hardware instruction, right? Is it, or a lot of the work seemed doable in combinational logic, it just isn't very well suited to the current instruction set? Or is that not true?
I have to give it a thought. Like so, like like I implemented most of it in software, and as I also like did the implementation in like porting the parallel bit extracts operations like to JVM like primitives. I didn't like think further about that. Like if like combined like hardware instructions would be suitable. Maybe they are. I have to give it a thought. Yeah.
Any other questions?
What about comparisons to non-functional data structures? I mean, Java and Guava in particular, the Google library for Java, has multi-maps. So how do they compare?
It's a different breed of multi-maps. It's a different breed of data structures. So my work is based on hash tries, which are like so-called persistent data structures that are like immutable data structures that you can efficiently update, or you can efficiently derive new variants from that. And Guava like doesn't have persistent data structures, but immutable ones. Yeah, so that's the main, I would say, like differentiation. So I was comparing to what is used in Clojure and Scala. It's also like there's recently a lot of for like normal data memory, and also like for database like generalized indexes. These kind of data structures are also used there. So that's more the area of inspiration, like where I was looking at. So.
Okay.
So it's, yeah, I don't have any performance numbers how it compares, but so I measured like once a comparison between these 3 data structures, and then also like the Java built-in ones, and maybe also like I think I also like compared to Guava. You have different trade-offs. So for example, things like iteration, like sometimes like in a continuous array, like you have better locality, and like here you have indirections because of the tree structure. So you cannot say like there's a win-win. It's like different performance trade-offs per operation.
Okay, thank you.